Welcome. My name is Gergely Dobrev and I will talk about our proactive scaling engine for Kubernetes. Nowadays, more and more services are deployed and managed in cloud environment. Cloud means on-demand access to network, compute and storage resources through internet. And managing a cloud application means to control the resource allocated to it. Kubernetes is a widespread container management platform which enables the deployment and management of scaling of such cloud applications. Allocation of resources can be a challenging task in case of cloud applications because the application has to meet the SLA requirements. However, the application provider wants the operational cost of the application to be minimal. Therefore, we can say that there is a trade-off between the SLA violation and the cost of running the application. Another aspect of the application management is that how complex is the configuration. The more parameter needs to be set to configure the application, the more difficult to find the optimal configuration. And if the application is running with a suboptimal configuration, then the SLA violation or the cost will be higher than expected by the application provider or both. Therefore, our goal is to simplify the management of cloud applications by providing easy-to-understand management parameters and to improve the auto-scaling functionality of the Kubernetes system. In order to test and validate our models and algorithm, we ran the simulations and the experiments with anonymized web traffic traces collected in a university campus network for a week in the middle of a fall semester. The dataset contains the flow count per second for Facebook traffic. In the figure, you can see that the daily seasonality of the dataset, and with green line, the data used during the training can be seen, and with red line, the test data. Our test application was an Nginx web server that served static HTML files. To have a high-level overview, we hereby present the structure of our presentation. First, we introduce a simple, easy-to-understand application management parameter which can be used to easily configure the application. Then, we present our models of the current operation of the Kubernetes autoscaling, which were used in large-scale simulation and to compare our proposed solutions. And in the last section, we present our AI-supported solution called HPA Plus. We show the used forecast methods, how our adaptive operation works, and the results of the comparison with HPA. Our first goal was to simplify the application management and give a simple parameter to control the scaling of the application. Therefore, we created a parameter called access, which can have a value between 0 and 1, and it describes the average resource utilization we want to keep for our application. 1 means that we want the applications to have a 100% resource utilization. Normally, we do not want to do that, of course. And for example, 0.5 means that we keep our application at 50% capacity. By setting this parameter, we define the over-provisioning of the resources for our application. It can be seen that this parameter specifies the trade-off between resource reservation and SLA violation. We defined 3 application management profiles with a specific access value based on our experience and measurements. Conservative strategy means that scaling actions are triggered to keep resource utilization at 85% of capacity. This strategy is wasteful in terms of resources, but leads to a negligible amount of SLA violations. Normal strategy is a compromise strategy that keeps a balance between utilization and SLA violation. Scaling is performed to keep resource utilization at around 90%. Best effort strategy is a resource-saving strategy that scales only if the system is under heavy load, meaning keeping the utilization at 95%. on average. Thus, SLA violations are certain, but running the application is close to the cheapest possible in terms of allocated resources. In order to be able to compare our solution with the default autoscaling functionality of Kubernetes, we created two models of the current operation. The Kubernetes default autoscaler, called HPA from Horizontal Pod Autoscaler, is a simple CPU threshold-based scaling algorithm. It periodically measures the CPU usage and uses a predefined threshold to set the number of new pods. For example, in case of a web application, when the number of HTTP requests increase, it follows that the CPU usage also increases, which is detected by the HPA controller. The controller then sets the number of new pods according to the measured CPU usage. We created two models to capture the characteristics of the HPA. The first one models the HPA as an MMPP/M/C and the second one is a discrete time model, which is a decision process. Both models have their pros and cons. The first one is simple and can be handled analytically, but the request timeout is not taken into account, and we have to have other restrictions and assumptions too. The second, the discrete time model, is more complex, difficult to handle analytically, but the request timeout is considered, which is possible, for example, in case of a web server when it is overloaded. Moreover, our simulations and measurements showed a good approximation to the HPA in general. In this slide, we present the results of comparing our discrete model and the HPA. With green dashed line, our model can be seen, and with blue line, the HPA can be seen. The top figure shows the number of pods at a certain point of time during the simulation, and the bottom figure shows the resource usage up until that time. It summarizes the running time of the pods which were in the system up until the current time. It is a resource function which can be used to compare the HPA and our model. As it can be seen in the figures, our model is a good approximation to the current operation of the HPA. In order to achieve more effective resource usage and higher service quality than the reactive HPA, our second goal was to create a scaling method that anticipates future requests and allocates or releases resources in advance. The behavior of the default HPA is reactive, which means that the scaling occurs only after the arrival rate changes. This means that the number of lost requests may increase in this period. Our idea was to implement our solution named HPA Plus, since we use machine learning models to predict the number of incoming requests, and the scaling is performed based on these predictions. Our solutions becomes proactive. We used three different models, one simple and two complex methods. The first model is a autoregressive model which assumes a linear relationship. The advantage of using this algorithm is that it is fast and has a low footprint. However, it is quite sensitive to peaks. The second model that we used is an LSTM network, which is a neural network. And the advantage is that it can model non-linear relationship and can learn the daily trends better. However, it takes more time to train this algorithm. The third model we used is the hierarchical temporal memory, which is also a neural network, and it is robust to noise and capable of online learning. On the other hand, this model has many parameters to tune, which is a disadvantage. We trained these models on the previously mentioned campus traces dataset, and after training these models, simulations were performed. On the left diagram, the cumulative request loss ratio is displayed. At the beginning of the simulation, HTM performed best in terms of loss, and AR was the worst one. However, at the end of the day, AR finished with the lowest value, and LSTM performed the worst. On the right plot, the cumulative relative pod usage in excess compared to the perfect forecast is shown. At the beginning, AR is the closest, but towards the end of the simulation, LSTM gets closer to optimal. From these results, we concluded that there is no single method that would always lead to optimal scaling. In fact, as the input traces show variable dynamics, selected methods perform better or worse compared to each other. This is why we decided to create a scaling engine in which several AI methods compete with each other, and the active method is chosen based on its performance on the recent inputs. Our proactive scaling engine, called HPA Plus, contains these 3 AI models that predict the incoming requests for the next minute. Each minute, the engine calculates the accuracy of the forecast models and select the best one. Based on the prediction of this best model, it computes the required number of pods for the next minute. If the accuracy of the models are poor, it switches back to the default HPA. We tested the implemented HPA Plus system in a real-life scenario with different scaling strategies and compared the results to the native HPA. Different scaling strategies correspond to different access parameter values. This parameter is used to control over-provisioning. The diagram shows the moving percentage of lost requests and the sum of pod minutes for the default HPA and the HPA Plus. Pod minutes describes the total cost of reserving resources. Comparing different scaling strategies, we can conclude that there is no significant difference in pod usage. However, it is clear that the lower the access parameter value, the fewer lost requests the system will experience. We observed that the proposed access parameter correctly controls the resource utilization in the experiments for both HPA Plus and HPA. In this diagram, we examined the case when the resource usage of HPA and HPA Plus were similar and compare the loss. It can be concluded that even in the case of similar resource usage, the number of rejected requests of HPA Plus is smaller than HPA's, which means that the competitive operation of HPA Plus results in more efficient management of the same amount of resources. Summarizing our work, we proposed a novel solution for resource scaling of cloud applications, which is an important management task. As our first goal, we focused on easy configurability and introduced a simple management parameter called access parameter, which is capable of controlling the resource allocation policy. Our second goal was to create a scaling method that anticipates future requests and allocates or releases resources in advance. Firstly, the currently available horizontal autoscaler was investigated and an analytic model was proposed, which was used to perform simulations. Secondly, we designed and implemented a novel proactive scaling engine, including multiple AI-based forecast methods in order to be able to optimize the operation in different circumstances. We found that our enhanced autoscaling engine called HPA Plus, is able to significantly decrease the number of rejected requests at the cost of slightly more resource usage. Thank you for your attention.